My dear students, today the topic of discussion is on bending stress, which is under strength of material PCME 403. Before going to discuss the bending stress, we have to assume few assumptions in the case of pure bending. The assumptions are: number one, beam is initially straight and has a constant cross section. Number two, beam is made of homogeneous material and the beam has a longitudinal plane of symmetry. Number three, resultant of applied loads across the transverse section is zero. Number four, the geometry of the overall member is such that bending, not buckling, is the primary cause of failure. Number five, value of E, that is modulus of elasticity, is same in tension and as well as in compression. Number six, plane cross section remains plane before and after the bending. And number seven, elastic limit is not exceeded. And number eight, deformation due to shear force is neglected. Now in the case of pure bending, if you see the diagram, so this is the diagram of overhanging beam. This overhanging beam is subjected to 2 point loads at the two extreme ends. That is, W and W are the 2 point loads, A and C are the 2 points. So from the shear force diagram, it is clear that the part BC having no shear stress or shear force. So this is only for pure bending. Now if you go to the next diagram, that is the governing equation of bending stress, derivation of relationship between bending stress and the radius of curvature. Considering a small length dx of the beam and AC is the part of the beam of length dx and subjected to bending as shown in the figure A. Due to bending, the beam will be deflected and the diagram is B. Due to action of bending, the length dx will be deformed and that length will be increased. Now if N is the neutral axis. Now what is neutral axis? Neutral axis is nothing but the axis which is passing through the neutral layer. Now neutral layer is the layer which is not subjected to tension and as well as compressive force. Now R is the radius of curvature. Now the layer GH after bending, which will be converted to G dash H dash, now the length will be increased. After bending, from this figure it is clear that G1 H1 will be R plus Y into D phi. Now change in length of the element dx, that is H1 G1 H1 minus GH, that is finally Y D phi. Now the strain on that layer, so that is nothing but the deformed length divided by original length. So after deformation divided by original length, so finally Y by R. The stress acting on such the element, that is dx, is given by, that is sigma, is nothing but from the Hooke's law we know that sigma equals to E into epsilon. So finally sigma equals to E into Y by R. So where E is the modulus of elasticity, Y is the distance from the neutral axis and R is the radius of curvature. From this it is clear that the stress directly varies with the distance from the neutral surface of the beam. Now from this diagram 1, it is clear that it is the part of the beam and it is the NA is the neutral axis. So just above the neutral axis, the portion is the subjected to compressive force and the below that, that is the tension. And the diagram 2, that is the transverse section of the beam. Now we consider a small elemental area dA that is a distance y from the neutral axis of the beam. Now the force on the small area, that is stress into area, that is sigma into dA. So the value of sigma equals to Ey by r into dA. As in the case of pure bending, the integral over the entire area must be 0. So there is no axial force acting on the beam. Now after integration we will get that E by r integration of y dA equals to 0. So E by r, this is the constant term that is not equals to 0. So obviously integration y by dA, integration y dA equals to 0. So y dA, integration y dA is nothing but A into yc. So as A is the total area of the cross section, so this is not equals to 0. That's why yc is the 0. So under pure bending, the neutral axis of the cross section passes through the centroid. Now moment of the elementary force, that is sigma elementary force, that is sigma dA about the neutral axis, and integrate it over the whole cross section area. So moment is nothing but the force into area, integration of that over the entire area. So finally we will get moment is nothing but E by r integration y square dA. So this y square dA is the area moment of inertia of the beam cross section about the centroidal axis. So this is nothing but the second moment of area or moment of inertia. It is denoted by the symbol I. So m equals to E by r into I. So 1 by r equals to m by ei. So finally we will get sigma equals to my by I. Now if the distance of the topmost fiber of the beam from the neutral axis is C1 and bottommost fiber is C2, in that case the maximum bending stress sigma 1 is mc1 by I and sigma 2 equals to mc2 by I, where I by C1 equals to Z1 and I by C2 equals to Z2. So Z1 and Z2 are the section modulus for any regular geometrical cross section. So finally sigma equals to m by z, that is called sigma max. Now there are two cases, one is for rectangular section and another is for circular section. In the case of rectangular section, where b is the width and h is the height, so I equals to bh cube by 12 and c1 equals to c2 equals to h by 2. So from that z equals to 1 by c1 equals to 1 by c2 equals to bh square by 6, where z is the section modulus. Now finally sigma equals to 6m by bh square, that is sigma max. Now from the circular section of diameter d, where I is the moment of inertia, that is pi d to the power 4 by 64. So c1 equals to c2 equals to c equals to d by 2. So z equals to 1 by c. So sigma equals to 32m by pi d cube. Finally sigma by y equals to m by I equals to E by r. So this is known as flexure equation of beam, and the whole theory is developed for pure bending. Thank you.